Welcome back, class. So last time we were studying about the Z transform, and we learned about the region of convergence of the Z transform. We solved the different examples. We have looked about at what will be the case for the stable system. Okay, so if the region of convergence includes the unit circle, then our signal will be stable. Okay, so for example, in this case, this is our pole and the region of convergence is this. So this is including the unit circle, so that our system will be stable. So we have seen the different cases. So now we are going to learn about the properties of the Z transform. So like the properties of the Fourier transform, discrete-time Fourier transform, which we learned in the last chapter, Laplace transform. So similarly, we have the properties of the Z transform. So the first property is linearity. Linearity is, for example, if we have one signal and if we take its Z transform. Okay, let's say there is one signal. If we take its Z transform, we get x1 of z. And if we have another signal, and if we take its Z transform, and we get its Z transform x2 of z. Now if I add these two signals and I want to calculate their combined Z transform, okay, so that will basically, the one way is first I add them and then I calculate the Z transform. The linearity property told us that is basically equal to the individual Z transform of this signal plus the individual Z transform of this signal. So simply take the original Z transform of the first signal, original Z transform of the second signal, okay, add them, that will be basically equal to the Z transform of the sum of the signal. Okay, so this is a basic property, first property, linearity. We will see the examples of each property in the live session. The second property is time shifting. Okay, so for example, if we have original signal and its Z transform is x of z. Now if we are having the time shift in that signal, okay, so basically Z transform will be remain same as of original signal, and we will multiply with the factor of Z, and it has the power of that shift. Okay, if this shift is negative, then the multiplication will become minus Z naught. Okay, Z ki power minus Z naught, and we will have the same Z transform of the original signal. Okay, so if we are getting the time shifted signal, what is happening? Original Z transform remains same, and then we just got a multiplication factor. Okay, here plus these are the basically the tells us about the initial conditions values. Okay, sometimes when we are actually doing the time shifting, we get these we should also include the shift due to the time shift if there is any initial condition values or not. Okay, we will see this with the example in the live session, that how we can actually calculate this thing. Okay, so the important thing which we should notice here is, if we are having the positive shift, then basically these values we can calculate. Okay, so we multiply z ki power n, so here we also multiply z ki power n, and then we take the summation of m is equal to 0 to n naught minus 1. Okay, for example, if the shift is plus 2, so basically this summation will become m is equal to 0, so n naught is 2 here, it's 2 minus 1 till 1. Okay, we have this in initial condition value. Okay, so then we can solve this and we can add the relevant initial conditions here, and if we get negative, multiply with negative. Now the summation is from minus n naught to minus 1. Okay, for the negative case, this is important. We will see the examples and then it will become more clear. Third property is frequency scaling. Okay, if the simple signal have a Z transform of x of z, and if we are multiplying in time domain with an exponential signal, okay, for example, a ki power n, 2 ki power n, half of power n, okay, like that. So if we are multiplying with an exponential signal in frequency domain, okay, so what we have to do here in the time domain, basically we will replace, for example, original signal has a Z transform of this one, so if you multiplying with exponential power n, now in frequency domain what will have, I will take the same original Z transform and just replace the Z with Z over A, whatever multiplication scaling frequency scaling factor I have. For example, if I multiplying with the 1 over 2 to power n my original signal, so whatever z transform of the original signal I have replaced with z over a. Okay, 1 over 2. Okay, and if you multiply the signal with n in frequency domain, okay, then basically this is equal to the derivative of the z transform in frequency domain. Okay, that is basically equal to the derivative of the original z transform in frequency domain. Okay, this is called differentiation with respect to z. Okay, or multiplication with n in frequency domain. Okay, so like if original signal is being multiplied with n, so whatever z transform of the original signal you have, if you want to calculate the z transform of this complete signal, so just take the derivative of that, okay, and multiply with z. Okay, and for the solving of the differential equation, difference equation, z transform properties, okay, sometimes we need the initial value. Okay, initial value means the x of 0. So whatever z transform of that signal you have, okay, just take the limit approaching to infinity, okay, and just solve that. So that will basically give us the initial value. And if you want to calculate the final value, so take the limit from z to 1, multiply your z transform with 1 minus z power minus 1, okay, and then just put up this limit and you will get the final value. Convolution, very important property, but very simple property again. Okay, like if two signals are convolving in time domain and you want to take their z transform, so this will be equal to the original signal z transform, second signal z transform, and then multiplication in z transform domain or frequency domain. So convolution in time domain is basically is equal to the multiplication in frequency domain. Okay, so let's say for example the convolution of the input signal we represent using y of n. So basically this is equal to, in frequency domain, its z transform and its z transform, its z transform, their multiplication. Okay, and if I write h of z, which is basically the ratio of the output z transform over input z transform, this is called transfer function, ratio of the output over input. But this is also called transfer function or also called system function of the z transform. System function of z transform. Okay, ratio of output z transform over input z transform. This is the table of the properties. Okay, all properties like we have discussed, more of them: linearity, time shift, okay, multiplication with exponential, derivative in z domain, okay, and also the initial value, final value, and these are the more properties. And general z transform table, we have learned that if we have the impulse, its z transform is 1. If we have unit step, its z transform is 1 over 1 minus z1. We have exponential signal, we solve this, okay, right, in these two examples. So it's basically 1 over 1 minus a z inverse 1, okay. And if we get, this is a positive side signal, this is a negative side sequence, okay. So the z transform was same, the only difference was in the region of convergence of that, okay. So this is the complete table of the z transform, which we actually can use to solve the different properties problems. Examples we will see in the live session. And if you want to take the inverse Z transform, so we can actually use the formula also, but using formula is quite complex approach. So basically we use two technique: inspection based technique. Inspection based technique is, for example, if your Z transform is becoming like this one, so you know that, okay, from the table we can find that this is basically is equal to the, in time domain, this is the sequence. So by inspection you can find that, okay, if we have simple Z transform output. But if it is a complex one, so we can use the partial fraction technique, okay. So we will try to simplify them in these forms, and then from these forms we can actually find the inverse, the relevant pair of that sequence, okay, to find the inverse Z transform. There are examples relevant to difference equation, convolution. We will see the LTI system. I have like explained you the ratio of the output Z transform and the input Z transform. This is called transfer function of the DT LTI system, discrete time LTI system. This is also called as system function of the LTI system. Okay. And if we are having the difference equation, so basically we can also find the Z transform, the output Z transform of the difference equation, which will be basically equal to this one. Okay, we will see this, that how we can actually drive this. So the more important thing than derivation is the using of these formulas. Okay, to solve the examples. So examples again we will see in the live session. So the last thing of this lecture is zeros and poles. We know that if we get a transfer function like in this form, so like the denominator, this is basically the zeros of this system. Okay, zm, z, like if we get z minus 2, z minus 3, or z minus 4, or z minus 1. So these are the zeros of my system. Like 2 and 3 are zeros, 4 and 1 are poles of my system. Okay, so basically if you know the zeros and poles, we can also easily identify the stability of the system, like we have learned earlier on about the ROC. So discrete time LTI system is stable if all the poles are inside the unit circle. So if you get one unit circle, if all of your poles are inside of that, your system will be stable. Okay, the system will be unstable if at least one pole is on or outside the unit circle. Okay, like at least one pole is on the unit circle or outside, wherever, the system will be unstable. Okay, this is equivalent to the like if you compare to the continuous LTI system. If you remember in the S plane, we make the decision that if all poles are in the left hand side plane, our system will be stable. So this is equivalent to that. If all poles are inside the unit circle, our system will be stable. So this is another way to quickly check the stability of the system. So that is the end of the lecture. We will solve the examples of each property and all other relevant example in the live session. Thank you very much for your time.